At exactly 8 o'clock in the morning, Coordinated Universal Time, something impossible happens. Every satellite navigation signal disappears. The satellites are still above us. They have not exploded, there is no flash in the sky, no warning siren, and no dramatic countdown on television. They simply stop being useful. On millions of phones, the blue location dot freezes, disappears, or suddenly becomes uncertain. Navigation apps can still display their maps, but they no longer know exactly where you are. Drivers miss exits. Delivery riders begin calling customers for directions. Ride-hailing apps struggle to match vehicles with passengers. Ships and aircraft receive navigation warnings. But these are only the most visible effects, because the first thing the world loses is not direction. It is time. Before we continue, one important clarification.
GPS is technically the satellite navigation system operated by the United States. Other systems exist, including China's Beidou, Europe's Galileo, and Russia's GLONASS. Many modern phones and professional receivers can use several of these systems at the same time. So for this thought experiment, when we say GPS disappears, we mean that the entire global layer of satellite positioning, navigation, and timing becomes unavailable for 24 hours. Every major satellite navigation system goes silent. What happens next? To understand that, we first need to understand what GPS really does. Thousands of kilometers above Earth, navigation satellites continuously broadcast radio signals. Each signal contains two crucial pieces of information: where the satellite is and the precise time at which the signal was transmitted. A receiver on Earth compares signals from at least 4 satellites. By measuring how long those signals took to arrive, it calculates 4 unknowns:
latitude, longitude, altitude, and the error in its own clock. That final measurement is easy to overlook. GPS is not simply a map in space. It is also a global clock distribution system. Each GPS satellite carries atomic clocks. Its signals allow receivers around the world to obtain extremely precise time without owning an atomic clock themselves. That shared time helps synchronize communication networks, financial systems, power infrastructure, scientific instruments, and transportation systems. The modern world does not merely use GPS to discover where things are. It uses GPS to make distant machines agree on when now is. In the first few minutes of the outage, most people experience inconvenience rather than disaster. Your phone does not become useless. It can still estimate its location using nearby Wi-Fi networks, cellular towers, motion sensors, and previously stored information. A car may continue estimating its movement using wheel sensors and an inertial navigation system. But these alternatives are not universally available, and they do not provide the same consistent global accuracy. In open rural areas, at sea, or high in the air, the loss becomes much more obvious. Digital maps still exist. The roads do not disappear from the screen, but the moving dot that connects the map to the physical world becomes unreliable. Ride-hailing platforms begin receiving vehicles in the wrong locations. Delivery estimates become less accurate. Fleet managers lose real-time visibility of trucks. Drivers who have depended on turn-by-turn navigation for years are suddenly forced to read road signs, call dispatchers, or stop and ask for directions. Nothing has collapsed yet. But the friction begins accumulating immediately. At airports, the situation is serious, but aircraft do not simply fall from the sky. Commercial aircraft use multiple navigation systems. Depending on the aircraft and route, these can include inertial navigation, radio beacons, radar guidance, conventional instrument landing systems, and instructions from air traffic control. Backup systems exist specifically because a single failure must not bring down an aircraft. The problem is capacity. Satellite navigation allows aircraft to follow precise and efficient routes. Without it, controllers may need greater separation between aircraft. Some approaches become unavailable. Flights may be redirected toward airports with conventional landing systems. Routes become longer, workloads increase, and delays spread across the network. The safest response is not to continue operating normally. It is to slow the system down. Departures are delayed,
Some flights are canceled. Aircraft already in the air are guided towards suitable airports or transferred to alternative navigation procedures. The skies do not become empty. They become less efficient, more crowded from the controller's perspective, and far more expensive to manage. At sea, the pattern is similar. Large commercial vessels do not rely on a single navigation screen. They also carry radar, gyro compasses, electronic and paper charts, depth information, and trained officers. In the open ocean, a ship can continue moving, but near a crowded harbor, narrow channel, or dangerous coastline, precise positioning matters enormously. Port authorities may slow or suspend some vessel movements. Ships wait offshore rather than enter a congested harbor without reliable satellite navigation.
Search and rescue operations become harder. Locating a vessel in distress takes longer. Automatic position reports may be degraded. Fishing fleets, survey vessels, and offshore operations lose tools they use every day. Meanwhile, the interruption begins spreading across the land. Modern farming uses satellite positioning to guide tractors, map fields, control planting, apply fertilizer, and avoid repeatedly covering the same ground. Without satellite navigation, many farmers can still work, but precision operations slow down or stop. Construction, mining, surveying, and mapping teams face similar problems. Machines still run, workers still know how to operate them, but centimeter-level positioning is suddenly unavailable. The immediate result is not famine or industrial collapse. It is lost efficiency. And in a world built around precise schedules, small losses of efficiency do not remain small for long.
Trucks arrive late. Containers miss transfer windows. Warehouses receive incomplete information. Ports process fewer vessels. Flights move fewer passengers and less cargo. The physical supply chain continues to exist, but its digital coordination begins to weaken. Then comes the less visible problem: time synchronization. Cellular networks need precise time to coordinate base stations, manage radio frequencies, and transfer users from one part of the network to another. When satellite time disappears, many systems do not fail instantly. They enter a condition known as holdover. Their local clocks continue running. High-quality systems may have atomic clocks, disciplined oscillators, fiber-based time sources, or other backups. These can remain accurate for hours, days, or even longer. But not every organization has the same equipment. Not every backup has been tested. And not every clock drifts at the same rate. That means the outage does not produce one clean, simultaneous failure. It creates thousands of systems slowly moving out of agreement with one another. For several hours, most mobile networks continue operating. But in areas with weaker backup systems, engineers may begin seeing synchronization alarms, degraded handoffs, reduced capacity, or unstable services. Calls and internet access do not vanish everywhere at once. Instead, reliability becomes uneven. One district appears normal. Another experiences dropped calls. A third loses accurate emergency location information. Network operators begin moving traffic, disabling non-essential equipment, and deploying portable timing sources. The world remains connected, but the connection becomes less predictable. Financial networks face a different version of the same problem. Modern markets process enormous numbers of events in extremely short periods of time. Accurate timestamps help determine the order in which trades, messages, and transactions occurred. They also provide the audit trail required to investigate disputes and irregularities. Banks and exchanges do not rely blindly on a single satellite receiver. Major institutions use local clocks, network timing, redundant systems, and strict monitoring. But as those clocks begin to disagree, confidence in the sequence of events becomes more difficult to maintain. Some institutions may widen their timing tolerances. Others may reduce automated activity or temporarily suspend the most time-sensitive operations. Your bank account does not disappear. Cash machines do not universally stop working. Ordinary card payments may continue through systems with functioning backups. The danger is more subtle. When billions of transactions occur across machines that no longer share exactly the same time, proving what happened first becomes harder. In finance, a tiny difference in time can become a very large difference in money. The electrical grid also continues operating. Losing satellite navigation does not automatically switch off power stations. Electricity is generated and distributed through many layers of protection and control. But precise timing helps grid operators compare measurements taken at distant locations. It helps them observe how disturbances move through the network, locate faults, and reconstruct the chain of events after something goes wrong. Without that shared time, operators lose some situational awareness. For 24 quiet hours, this may remain manageable. But if a major line fails, a storm damages infrastructure, or demand suddenly changes during the outage, diagnosing the problem may take longer. Systems with strong, independent timing continue functioning. Systems built around a single timing source become more vulnerable. The GPS outage does not necessarily create the second disaster. It makes the second disaster harder to understand and contain. 6 hours into the outage, the world is still functioning. The lights remain on in most places, aircraft are landing, ships are moving, people are making calls and buying food. But nearly every system is operating with less confidence and more manual intervention. Emergency services receive location information that is less precise. Dispatchers ask callers to describe nearby buildings and street names. Rescue teams return to maps, radio directions, and visual landmarks. Drones used for inspection, mapping, and delivery remain grounded unless they have reliable alternative navigation. Scientific networks begin losing a common reference. Seismic sensors, weather instruments, and distributed research equipment depend on accurate timing to compare events occurring far apart. Data centers and internet companies rely on several sources of time, not only satellites. Most of the internet does not simply disappear, but clock errors can confuse logs, security systems, distributed databases, and automated processes. Engineers become reluctant to trust the timestamps shown on their own screens. This may be the strangest effect of the entire outage. Humans can look at a clock and accept that it is a few seconds wrong. Machines cannot always do that. A machine needs to know whether a message is new or old, whether a security certificate is valid, whether an event happened before or after another event, and whether two measurements belong to the same moment. For a human, time is an experience. For a computer network, time is part of the evidence. After 12 hours, the disruption becomes deeply unequal. Organizations with atomic clocks, terrestrial navigation systems, fiber timing connections, disciplined oscillators, trained operators, and tested emergency procedures continue functioning. Organizations that treated satellite signals as an invisible service that would always be available begin running out of options. Large airports manage the crisis better than small airfields. Major telecom operators move traffic more effectively than isolated regional networks. Modern ships with trained crews adapt more easily than small vessels built around consumer electronics. The true dividing line is not between high technology and low technology. It is between systems with redundancy and systems without it. For decades, satellite navigation has been so accurate, so widespread, and so inexpensive to use that it gradually became invisible. Companies removed older equipment. Training programs became shorter. Paper procedures were forgotten. Backup systems were postponed because the primary system almost never failed. Efficiency increased. So did dependence. Now, for the first time, the cost of that dependence becomes visible. 24 hours after the outage began, the signals return. Phones begin reacquiring satellites. Ships recover precise positions. Aircraft navigation systems confirm their integrity. Timing receivers reconnect to the source they have been waiting for. But recovery is not as simple as switching everything back on. Networks must verify that the returning signals are real and accurate. Clocks that have drifted cannot always be moved instantly without disrupting logs and databases. Some systems must be resynchronized gradually. Airlines face canceled flights, misplaced crews, and passengers in the wrong cities. Ports face waiting vessels and missed schedules. Delivery companies face warehouses filled with late packages. Engineers must examine every alarm produced during the outage. The signals return in seconds. The backlog takes days to clear. And yet, the world has not ended. Civilization survives because pilots, sailors, engineers, dispatchers, farmers, technicians, and emergency workers still know how to make decisions when automation disappears. The most important lesson is not that GPS is weak. It is that modern civilization has transformed a collection of faint radio signals from space into a global public utility. We use those signals to guide vehicles, distribute atomic time, coordinate machines, document transactions, and make distant systems behave as parts of one enormous network. Most days, nobody notices. There is no wire running from an atomic clock in space to your phone, no visible connection between a satellite and a power station, a mobile tower, a tractor, a shipping container, or a financial exchange. But the connection is there. And if it disappeared for only 24 hours, the world would not immediately collapse. It would slow down. It would become less precise. It would become more expensive, more manual, and more uncertain. And for one day, humanity would discover just how much of modern life depends on knowing two things with absolute confidence: where we are and exactly what time it is. But satellite navigation is not the only invisible system holding the modern world together. Beneath the oceans lies another network, carrying almost everything we call the internet. And unlike satellites, those cables can be touched, damaged, and cut. So what would happen if the world's undersea cables suddenly went silent? That is the story of our next episode.